Hey everyone, I want to finish up lecture note 6. This is going to be a fairly quick lecture. This is the least squares assumptions for multiple regression. This is the end of lecture note 6 on page 10. So we had the least squares assumption in single variable regression. That got us the sampling distribution of the betas. We know that they're normal. The same is going to apply here. We're just extending the assumptions to multiple regressors. So notice in the model I've written down, we have x1, x2, and then the three little periods here mean that we have any number of regressors up to xk regressors. So this applies to a model with 2 regressors, 3 regressors, up to xk, where k could be 100 regressors. So here are the assumptions. The assumptions that get us nicely behaved coefficient estimates and that allow us to use regular t-statistics, p-values, confidence intervals, etc. So assumption number 1, the conditional distribution of u given all the x's has mean 0. So we've written that down here. The expected value of u, conditional on all the x's, is equal to 0, which implies the correlation between u and x, or any of the x's, is equal to 0 for all xk, for all x's in the model. So this is the same as the first assumption for the Gauss-Markov theorem when we had a single regressor. In other words, that our included regressors uncorrelated with the error term. If this assumption fails, then the correlation between the error u and x is not equal to 0. We have omitted variable bias, and that leads to biased beta coefficient estimates, which is obviously not good. So this is the main one we will deal with throughout the rest of the class, the one we care about when we talk about omitted variable bias and we talk about how to poke holes in regression analyses. We are going to be arguing that assumption number 1 fails or holds up. Assumption number 2, all the x's and the y, the dependent variable, are independently and identically distributed. So this is satisfied automatically if the data are collected by random sampling or a randomized controlled trial. Not necessarily satisfied with observational data rather than data you collect yourself. Assumption number 3, large outliers are rare. Remember from the single variable case, we said that if all the data points lie along a certain plane or within a certain bandwidth here, maybe all the data points lie within that bandwidth, the regression line would be the line in green, but maybe there is one data point that pulls up the regression line, the data point in red there, way up high. This is an outlier, and it's going to cause the regression line to be pulled up rather than where we think it probably should be, the green line. Now what's causing this? It could be that the red data point is a real piece of data that we need to keep in our model. It could be that there's somebody with fat fingers and they press an extra 0 or something when they're recording the data in Excel. We don't know beforehand, so we just have to think about what to do with that data point. Assumption number 4. Now this one's new because it didn't apply in the single variable case. It's called no perfect multicollinearity. So what is multicollinearity? It's when 2 of the x variables, x1 and x2 for example, are perfectly correlated. So I should have used, instead of a y here, I should have said x, we could say x2 is a function of x1, x2 equals 2 plus 3x1 with no error term. So it's an exact function. X2 is an exact function of x1. Another example would be maybe x1 is equal to percent English language learners. That's this this here. X1 is equal to the percent English language learners in the school district, and x2 is equal to the percent of native English speakers. So that's kind of a silly way to define this, but x2 is then equal to 1 minus x1. Another example of this is if we have x1 equal to 1 for males and 0 for females, and we define x2 as the opposite. x2 would be equal to 1 for females and 0 for males. Then they're just perfect functions of one another, and you can't include both of them in the model. You can only include one. So in other words, you cannot include a dummy for male and a dummy for female in the model. This is called the dummy variable trap. If you try to do this, your statistical package will drop one of the variables automatically. As a side note, we also have to be concerned about high imperfect multicollinearity. So the example above was perfect multicollinearity. We also need to think about imperfect multicollinearity when two of the x variables are highly correlated. Why would that be a problem? Well, so for example, if we're thinking about beta 1 is the effect of x1 holding x2 constant when both x1 and x2 are in the model, and if the correlation between x1 and x2 are high, there's very little variation left in x1 once x2 is controlled for. In other words, we have both x1 and x2 in the model. They're both basically the same variable. Controlling for one of them means that we don't really have much information left over in the other one to identify an effect on our y variable. So what this leads to is just really high standard error estimates on the coefficients, beta 1, beta 2. It's not going to lead to bias, but you'll get imprecise estimates, and the t-stats will be very low. P-values will be very high. So we have to think about that. Are these variables, the x variables, really correlated? Homoscedasticity and heteroscedasticity are the same as before. A rule of thumb should be you always assume heteroscedasticity and use robust standard errors. So R definitely has a setting where you can implement robust standard errors in your linear model rather than assuming homoscedasticity, and that'll be those will be fine for the situation when you actually have homoscedasticity, but that's almost never the case. So always implement robust standard errors. Okay, why are these important? With these assumptions, we know the sampling distributions of the betas. If all of these assumptions hold, we know that for each beta k hat, we know that each of them are consistent, and what that means is beta k is going to converge in probability to beta hat k is going to converge in probability to the true population value as the sample size grows. So we are going to get nice estimates of our betas if all those assumptions hold. We also know the sampling distribution of the beta hat k's, which is great because that means we can standardize them and compare them to the standard normal distribution, just like in a single variable model. So we have the standard formula here where we're going to subtract off the mean, and divide by the standard deviation. In this case, in practice, that turns out to be the standard error of beta hat k, and we know that this is approximately normally distributed with mean 0 and variance 1 by the central limit theorem. So great news, the t-stats and the p-values, confidence intervals the same as before. Thanks, central limit theorem.